Hello, everybody, and welcome to the second Engineering Integrity Society webinar in our series on hydrogen adoption across industries. My name is Niall Smith, and I'm a member of the Durability and Fatigue group of the EIS, and I'll be chairing this session today. This is the second webinar in our series. We've got two more on the 19th and the 21st of May, so I'd encourage you to register for those. Other upcoming events, we've got the Instrumentation Analysis and Testing Exhibition in Silverstone on the 12th of May, and that's free to attend. And we've also got a number of talks at that exhibition. We also have a seminar on manufacturing-induced imperfections, and that's on the 4th of June at the AMRC in Sheffield. And I'd encourage you just to keep an eye on the EIS website and LinkedIn for any other future events, and even consider becoming a member of the EIS. And we're always open to suggestions and future and ideas for any future events that you think might be worthwhile hosting. So today we've got two presenters, Vicki Wilkes from Darvick, who'll be first, and Khurram Amjad from UKAEA. If you joined last week's session, we did the questions through the chat, and I feel like that worked quite well. So if during the presentation, if you want to type your questions into the chat, and we'll get to them after the presentation. Unfortunately, Vicki couldn't join the call, but she recorded her presentation, and we have Darren Wilkes from Darvick, who's the technical director. So he'll be answering questions during the presentation. So I think we're ready to start the presentation.
Hi, welcome. My name is Vicki Wilkes. I'm the Commercial Director at Darvick Limited. I'm here to talk to you today about developing and validating test machines for hydrogen applications. So hydrogen is a key enabler for the transition into net zero, with applications spanning transport, aerospace, heavy industry, across the board. But with the introduction of hydrogen, there's the introduction of some fairly complex material and safety challenges due to hydrogen embrittlement. So accurate assessment of mechanical performance in representative and operational environments is essential for us to generate reliable design data for databases, predictive models, and for safety validation to bring materials into commercial application. And despite this growing demand, there still remains a recognised UK shortfall for commercially available representative mechanical testing. So this presentation will outline the development and validation of these test machines and methods to address this gap and the associated challenges. I will start by introducing Darvick. So why am I here? So Darvick is an independent subcontract mechanical test laboratory. We design and build machines, and then we offer that testing service to any customers who wish to have their materials or products tested. But we specialise very much in supporting research and development and material validation, especially in harsh and extreme environments. So that might be cryogenic temperatures or extremely high temperatures, could be in a vacuum or in a high pressure environment, in steam, and obviously in hydrogen. We have customers across a wide range of sectors, so aerospace, nuclear, defence, power generation, but also local manufacturing and small entrepreneurs. So we test everything from fence posts and horse saddles through to composite materials for jet engines. We have UCAS flexible scope accreditation, which basically means that we can perform a test to a customer's requirement or to a standard that's very unusual, and still give an accredited traceable test report, so it doesn't have to be a recognised international British standard. And I summarise that in 2 sentences. So we make stuff to break stuff, and it's never been done is what we do. So, hydrogen. What's the problem? So essentially at the moment with the developing hydrogen economy, there's an awful lot of research and development at TRL 123. So TRL is technology readiness levels, and that is a transition from something being a blue sky concept through to something that's actually in commercial application. So TRL 1, 2 and 3 is the academic applied research, and then 7, 8, 9 is where things are going into prototypes. But TRL 4 and 5 are where things are being tested in relevant and representative environments. And that capability, although there's lots of academic and lots of industrial demand, the ability to test in these environments is not evolving at the same pace. And there are lots of reports out there explaining about this. So ATI, MPL, the Royce Institute. And testing is a cross-cutting enabler, so it's sector agnostic, material agnostic. No matter what it is you're trying to do, if you want to take the same material in lots of different applications, it still has to be validated in those applications. So why have we got this problem? Well, we've got this problem because basically it's technically challenging, it's time-consuming and expensive to do this with hydrogen, not least because of the various health and safety concerns associated with it. So if it's so difficult, why bother? So obviously we know that hydrogen is an environmentally friendly solution for fuels and energy. But why does it have to be representative? What's so special about hydrogen? Well, the problem with hydrogen is that it brings significant challenges for materials, and that is hydrogen embrittlement. So without giving you a lecture in metallurgy, essentially what this means is it reduces the ductility of materials, and they may then fail suddenly with very little plastic deformation. What's also interesting about hydrogen is that the amount of hydrogen embrittlement is very much affected by temperature, pressure, the amount of strain or load on the particular material, and also the concentration or the purity of the hydrogen that it is in. So if you take an aircraft, for example, if they want to use liquid hydrogen in the storage tanks, which is at cryogenic temperatures, minus 253, then has to go through the entire propulsion system and out to the engine at the other end where it's burning. So it's extremely hot and it's gaseous. And if you can imagine, those combinations of temperature, pressure, strain are going to vary all the way through that system, as well as throughout the duration of a flight, from standing on a runway to taxiing to takeoff, cruise and landing. So you're going to have to replicate each of those different conditions to be sure that any component in that system is going to be safe for commercial application. And also with hydrogen, there is the explosion risk, which we've mentioned once or twice. So if we talk about the explosion risk, we all learnt when we were small children that you need 3 things to create a fire. So you're going to need oxygen, you're going to need fuel, and you're going to need something to ignite it. Which means that almost everything we do around designing a test machine to work with hydrogen is making sure that we have at least one of those not present. So we'll take the electrical systems on a control machine. So basically we need to avoid sparks. Everything has to be ATEX rated, which actually now in the UK is UK EX rated. It's very difficult to come up with a single standard or a single set of guidelines that you need to follow in order to say that something is safe, particularly if you're developing something that is new or unique. So everything has to have a lower power limit on the items, and that it depends on the zone rating, the ATEX zone, which is essentially down to the likelihood and duration of an explosive atmosphere. So if you're likely to get hydrogen there in any level, how much, how long, and how do you reduce the power? So you can buy components, so you can buy load cells and solenoid valves that are classed as intrinsically safe. So these are basically designed to prevent any sparks or heating that could ignite an explosive atmosphere, even if there's a fault, even if something goes wrong. The downside to that is that these tend to be more expensive. You've got limited choice. They could be on longer lead times. And even though we buy those where possible, where it's practical, you still can't design a complete system. You can't have your entire controls and interlocks made out of intrinsically safe items. So one of the other options that we use is a thing called Zener barriers in the system, which basically restrict the current and voltage to safe levels. So if anything tries to go above that, it'll shut down. But if you can imagine, in a test machine, we're measuring very, very sensitive, very accurate levels. So if you take an extensometer for measuring strain, what we found when we put the Zener barrier into the system is that actually has an effect on that extensometer reading. So we spent quite a lot of time actually validating what that effect was, so that we could still then calibrate that extensometer and give valid readings. Luckily, it was a very linear effect, so we could account for that and we could take it out. But it's all the sort of additional research and development that you have to do when you're validating a machine to work with these components that are safe for use with hydrogen. So if we do get a spark, if for some reason we have a metallic component that fails when we're testing it because we're testing it to destruction, we want to ensure that there's not enough hydrogen to ignite. So this brings us on to gas handling, and gas handling is basically extraction, purging and venting. So when you're using hydrogen, you have to make sure that before you introduce hydrogen into a system that you have purged it. You've got rid of all the oxygen in there. As we said, oxygen is not what you need, not what you want for a fire. So you use inert gases. So that's normally argon or nitrogen or and basically you push these inert gases through the system, make sure you've got all the oxygen out, and then you tend to retain these inert gases around the area where you've got your hydrogen, so that even if the hydrogen leaks out of your sample, it goes into an inert atmosphere, which is at a higher pressure. And essentially all of these mean that you've got complicated gas systems, so independent sets of monitors, interlocks, flow measurement, pressure measurement, making sure that it's there, that if there's a fault with that, then it closes off the hydrogen. So it means that all of these gas handling systems are complicated. There's a fairly simple solution to ensuring that you don't get too much hydrogen buildup, and that is ventilation. So this is an example of a machine we're building at the moment that will use liquid hydrogen, and it's going down to an airfield, and the real basic solution is very large vents in the side, so that if any hydrogen escapes out of that frame, but despite all the safety features, it will disappear. It will not be able to build up to such a high level of concentration that it could possibly explode. There is also another advantage of hydrogen, and that is that if it does happen to escape, it tends to rise. So as you can see here, we've got our safety sensors and we've got our extraction at the top of the machine. It's not going to build up from the ground out. It's not going to flow out underneath all around the lab and accumulate. It will tend to rise, and if you can get it to go out of the building and up, then it's good to go. So, how do we keep the hydrogen in? At Darvick, we have a lot of experience in sealing systems. We've built environmental chambers for about 20 years, but hydrogen is well known for being particularly good at wanting to escape. So sealing of hydrogen is one of the big technical challenges. So if you look here, we have hollow sample. We do hollow sample testing at the moment, and it's relatively straightforward. Basically, it's a cone type assembly. The beauty of the cone, which is to our design, but the beauty of that is that we can vary the size of the samples, so you don't just have to have one fixed interface. You can have different diameters if you want. The other technique is double sealing. So basically in a chamber like you've got on the right hand side, you can see the double seals, and we will have an inert gas that runs in between those seals. So again, if the hydrogen gets out of the sample into the chamber, that inert gas will ensure that it stays in the chamber until it's extracted through the proper and safe system. But the other question is really how you are measuring hydrogen. So as I said, the actual purity of the hydrogen is extremely important to the amount of embrittlement and the effect it has on the material. So most tests look for an N5, so that's 99.999% pure hydrogen. But by the time you've put that through a test system, through various pipes, valves, seals, through the sample itself, can you be confident that you've still got that same purity of hydrogen at the end of the test as you had at the beginning? So if you're testing in a hollow sample, that's relatively straightforward. You know exactly where that hydrogen's coming through. You know how you can measure that. If you've got a solid sample and you're pumping the hydrogen into a chamber around it, you can put a capillary tube into the chamber and then take that off to your mass spectrometer, because they can't always withstand the pressures and temperatures that you're applying to your sample. So that again, it can be used. Where do you put the capillary tube? How straight is it? How long is it? So on and so forth. And then you've got the question, if you're trying to measure the permeation of hydrogen, so from the inside of a sample to the outside, in a vacuum, that is much more complicated, because the question is, you've got very, very low levels of hydrogen. So you've got to make sure that you've got enough resolution on your measurement equipment to ensure that you're picking up actual hydrogen coming through the sample. And where do you put that? Because where does that hydrogen travel in a vacuum? How is it going to move from the sample surface to your measurement sensor? You can't fill your entire chamber with sensors. You're reasonably restricted. So we're actually doing an engineering doctorate with Cranfield University at the moment on that exact question, so that you could be confident that what you're measuring is accurate and repeatable. Because if it's not, then it's really not giving you any useful information. And at the end of the day, we can put all the sensors and the mechanical and the technical bits in that we like, but these machines are ultimately going to be operated by people, and people are one of the biggest variations in any test lab. So you will try and automate a system as far as possible. This is one section of one sheet on a spreadsheet with about 15 pages that show all the different interlocks and fail safes and safety checks that we have on that system. Because you can't just shut a system down that's got hydrogen if you press an emergency stop, because it might be that actually you don't want to vent all of a sudden. You want to actually retain some of those external shield gases, so that you ensure the hydrogen vents the way you want it to. And actually sometimes with those interlocks, you're better not to have a sensor, because you then have to ensure that if that fails, is the system still safe? So for example, are you better just to have a manual lock on a door, and then have systems away from the machine to control entry and exit. So controlling how your people and how your safety features are going to work is quite a key feature of those hydrogen systems, and involves quite a lot of lengthy discussion amongst ourselves as to how exactly things are going to work. So that's a lot about considerations for developing test machines. Like I said, that there's many different aspects of it. Trying to summarise it in a short talk is quite difficult. But then we've got to validate these results and these machines. You know, is the result that we're giving accurate? And that has significant challenges too. So, for example, at the moment, hydrogen is such a new area, such an evolving area, that there are very, very few test standards, international procedures for carrying out hydrogen testing. And that's largely because of all the things that I've already said. People don't know how best to do it yet. There's also issues around calibration. So load calibration is okay. Load cells can be outside of the chamber. Pressure sensor validation, you can put those elsewhere in the system. They don't have to be subject to the extreme temperatures. But strain measurement, people want to do strain control testing. At the moment, to our knowledge, there is no actual calibration of extensometers in the very cryogenic temperatures and in the different atmospheres. And there is no UCAS accredited thermocouple calibration below liquid nitrogen temperatures, so below -196. The lack of test machines able to use hydrogen means that it's very difficult to get comparisons. You can't do round robin testing. There are no two machines the same at the moment. That's something that we're working on with other people and industrial partnerships. And there's no knowledge on the long-term degradation of sensors. How do we know that a sensor that we're using today is giving us the same results in 1 month, 2 months, 6 months? So those are all things that are still very much evolving. There's also very little regulatory guidance at the moment on what good actually looks like, what tests do a material or a component have to test for them to say that they're happy for that to then be put into a commercial application. So those are all sort of difficult things that we need to overcome to say that actually not only have we developed something, but we validated it internally with calibration, it can do the tests people want, and that it will give the results that people are looking for. There's some positive outlook. I have to say the Aerospace Technology Institute, with things like their SME programme, are acknowledging that we need to put some funding and support into this. There are lots of conferences, workshops, networks, this, for example, around the hydrogen economy and people talking to each other. And for us, for definite, you know, there's an emerging supply chain, there's a whole emerging community, and it's really exciting to be working and collaboratively with new people and new technology, and that's kind of ironically quite mutually beneficial. So we might test a sensor or test a seal in a hydrogen environment, and actually if it works really well, we could then look to incorporate that into future developments of our kit. And also that industrial and academic overlap. Hydrogen is such a specific challenge that you need that real scientific and fundamental understanding of the material behaviour linked to those industrial applications. So there's lots of good stuff happening. It's just not happening as fast as people really need it to hit the objectives and the timescales that are being talked about at the moment. So I guess in summary, the ability to test and validate in representative environments is critical to understand how materials genuinely will behave with hydrogen. But it is challenging. It is very challenging from a test machine point of view. And it would make it easier if we had that standardization and validation to really kind of be 100% sure about the results that are being generated. But that collaboration and cooperation across sectors and throughout supply chains is really important. So there's no point in every man and his dog testing the same material under the same conditions, because they won't share database information, especially where they are standard materials such as 316L. It would be really beneficial if everybody can get together and just say, right, I'll do this, and then we share the results, especially with the limitations on capacity and capability we have at the moment. Thank you very much.
Okay, so I'd like to thank Vicki for that presentation. As I said, if you've got any more questions, I think Claire is from Darvick, so she should be able to answer your questions. I think Darren might be on the chat, so I'd encourage you, if you've got any questions, just ask them in the chat, and they should be able to answer them. So we'll move on to our second presentation. So we've got Khurram Amjad from UK AAA. So if we would like to put the slides up.
Sure.
Thanks, Khurram.
Yep. Thank you very much. So my presentation would be about cryo-mechanical testing. I will be presenting the perspective from fusion industry, and I would highlight there's a significant overlap with the aerospace as well when it comes to hydrogen and cryogenic testing. So I'll kind of touch on that. I'll keep it to high level, not going into too much detail about the specifics of the testing, but then there are some results which we can then discuss perhaps in the Q&A as well. Okay, I'll start with a brief overview of fusion, because I'm aware some of you might not be have a level of familiarity with nuclear fusion and what exactly UK atomic energy does. So I'll start with the kind of the basic chemical reaction. So nuclear fusion is essentially a chemical reaction which powers the sun. We try to do it on Earth. And it requires a couple of conditions. So first is we need a material, so the lightest atoms that we can find, which is hydrogen. We have to heat them up to about 150 million Kelvin, and we have to confine them, which we do it through very powerful magnets. And given the right conditions, then they fuse together and produce helium with significant energy and very high power neutron as well. So as you can see, there's no, it's all safe in terms of the emissions, so we don't generate any carbon dioxide. And given we have abundant supply of hydrogen, then the cycle can be sustainable as well. We don't need any radioactive material. So which is why in theory, it's a sustainable process, which is why we are working towards developing nuclear fusion capability for power generation. So the mission of Atomic Energy Authority is to lead the delivery of sustainable fusion energy and to maximize scientific and UK economic benefit. So wherever there is an overlap with other industries, we would like to create an impact, and we actively look for opportunities where the technology that we are developing could be used in adjacent industries as well. And cryo-mechanical testing is, I believe, one area where we could create a cross-sector impact. So how do we do this reaction? There are various different methods of performing this chemical reaction to produce power. UK AEA specifically works with a method which requires a donut-shaped magnetic bottle. We call it tokamak. To kind of create the plasma to do fusion. So essentially, it's a vessel. It's a vacuum vessel. We heat up the fuel mixture, which is the isotopes of hydrogen, to very high temperatures, and then we confine. It's a charged plasma, so we can control it through very powerful magnets. In next generation tokamaks, the magnets will be superconducting, so they will operate around the liquid hydrogen temperature, which is around 20 Kelvin. So we use those magnets to confine the plasma and then try to sustain the reaction so we can produce energy from it. I have a picture here of the inside of the Joint European Torus, which was which has been a flagship fusion device for many decades, and it was based in a Khurram Science Center, which is UK's primary facility, and it got decommissioned. Well, it is in the process of decommissioning, but the operation stopped a couple of years ago. So just to highlight some of the key components of tokamak device, which we need to ensure that they operate in a safe manner under operating conditions, and we'll touch on the operating conditions in the next slide. So we have got the first armor, which kind of bears the wrath of the heat flux. So we are talking about up to 5 megawatts per meter square of heat flux onto these armor panels. And the primary material of choice is tungsten. And then on the back side, we have got structural material, typically a fusion variant of steel, to provide the structural support for these blankets. Then we have got these coils, which are superconducting magnets essentially. They operate from 4 Kelvin all the way up to 20 Kelvin temperature range. So they're obviously very cold. So we need to design them for cryogenic conditions. And then at the bottom, we have got a diverter. So this is one of the cassettes of a diverter. It essentially acts as a exhaust system for the fusion. So again, it has to take on a significant amount of heat. Also, it has got copper channels to take the heat away for power generation as well. So it performs multiple functions as well. And then lastly, we have got breeder blanket, which is, I believe, one of the most significant components of the device. So I mentioned about abundant supply of hydrogen. So we essentially look for two isotopes, deuterium and tritium. Deuterium can be extracted from seawater and it's readily available, but tritium is something we need to generate as we do fusion to make the whole fuel cycle sustainable. And this is where breeder blanket comes into play. So its role is to first of all shield the whole mechanism which could generate the tritium. So it will have the armor, and then it has lithium in it. The design is not yet finalized. There are multiple designs that are being considered, but essentially lithium, when interacts with high energy neutrons, generate tritium, and then we need a mechanism to retain this tritium and then extract it and then feed it back into the fuel cycle to make the whole fusion process sustainable. ITER, which is being developed in south of France, this is the next European kind of project for the fusion device after the JET. So this slot, they reserve the slot where they will be testing different designs of breeder blankets to determine their efficiency and their performance. And different countries are working on developing these breeder blanket that will be tested in the ITER program. Okay, if we come to the loading conditions that are experienced by components in this vacuum vessel, so we have got quite a significant range. So let's first talk about radiation-induced degradation. So as we do the chemical reaction of fusion, we generate very high energy neutrons, which are on the order of magnitude higher than the energy spectrum of neutrons we typically witness in the fission reactor. So they cause significant damage and embrittlement. Helium is also, when it generates during the fusion process, it has significant power, so it can cause transmutation in the material, uh, which leads to embrittlement, which is essentially reduction in ductility. And then hydrogen as well. It's a fuel, and we need to consider the hydrogen embrittlement as well. And we need to also look at specialized materials which are permeable so that we can transport the tritium and retain it as well. So there's a significant overlap there with the hydrogen, other applications of hydrogen. And then when we talk about heat loading, I think within a few meters, we are talking about significant temperature gradient. So from cryogenic at the outer shell, where we have a superconducting magnet operating at very cold temperature, um, to very hot temperatures in the middle of the vessel, where we have a burning plasma. So we are not just concerned about very high temperature, we are concerned about cryogenic temperature, we are concerned about temperature gradients, there are high heat flux loading, there is significant thermal cycling from start-stop of the device. There is a significant overlap with some of the conditions that we see in aerospace or aviation sector as well. And in terms of mechanical loading, so we do have body forces, we do have superconducting magnets, so we do have to consider electromagnetic body forces as well. There are dynamic and transient mechanical loads from the start and ignition of the plasma and the cool down as well. And we also have to consider the manufacturing residual stresses from the manufacturing processes, which alters as we start inducing thermal cycling to these materials. In last week's webinar, we do have a presentation from Louise Gale where she provided an excellent presentation on different loading scenarios for the jet hydrogen powered jet, and there is a significant overlap which I've highlighted in red here. So it's not just about cryogenic temperature. So when we talk about the whole cycle of the jet of the aerospace jet, the fuel system is at 20 Kelvin, and then you have got combustion, and then you've got a turbine as well. So I believe the temperature range that was specified in that presentation was from 20 Kelvin to 1500 Kelvin. And this is exactly the temperature range that we are dealing with in the nuclear fusion as well. So superconducting magnets at 20 Kelvin, and on the higher end, we have materials exposed to up to 1000 degrees of temperature. So we are also concerned about thermomechanical fatigue and thermal creep, which are the areas I believe aerospace sector is also looking at. Hydrogen embrittlement is again in the picture more at a higher temperature than at cryogenic temperatures. And then obviously residual stresses are there whenever there is a manufacturing process. So we need to consider that as well. So from fusion perspective, what our kind of medium-term goal is to develop a capability where we are able to test materials which are used in superconducting magnets. So we are talking about structural materials, typically 316L, and then superconductors, and then conductors as well, the conventional conductors like pure aluminum or copper, and then insulators, which are composites. So we have this need to test the whole range of materials from metallic to composites in relevant environment, which includes cryogenic temperatures. We are also trying to develop capability where we can do synergistic testing, where we have electromagnetic loading as well. And we are also working on diagnostic, which gives us full field deformation, so particularly non-contact camera-based techniques like digital image correlation. Okay, before I jump into the kind of our rigs, I'd like to kind of provide a brief overview of the standard methods for testing. So historically, when we talk about low temperature testing, we talk about liquid filled dewars and which are fitted onto the load trains. And in these traditional setups, the testing is limited to cryogen temperature. So for nitrogen, 77 Kelvin, and for liquid helium, it's 4.2 Kelvin. And if we somehow do it for liquid hydrogen, that would be at 20 Kelvin. Uh, uh, However, the requirement is not just at cryogenic temperature. As I said, the materials witness a range of temperature from very low all the way to very high temperature. So we need a capability where we should be able to see the material behavior over a range of temperature, not just at cryogen temperatures. And in terms of strain measurement technology, traditionally there is a reliance on clip-on extensometer, which essentially gives you a uniform elongation over the gauge section. There are clip-on extensometers for fracture toughness measurements as well, which you would use in your compliance measurements. And then for strain measurements at a given point, I think the industry standard is still the strain gauges. They've been rated to cryogenic temperatures as well. But the problem with it is if you have a material which shows heterogeneous strain fields, then I think you're limited by the number of data points you can get, because there is a practical limitation to the number of strain gauges you put on your sample or component. So ideally, we'd like to see a non-contact technique where you should be able to see the full field strain fields. And this is what we try to work on. So in our lab, we have got 3 different rigs that can do mechanical testing at low temperatures. So the first one is a Instron rig with the STS chamber. So that has a temperature range of minus 150 degrees centigrade to plus 550 degrees centigrade. And we have done extensive work on it to kind of deploy stereo digital image correlation on it. And I'll be presenting some results from this rig in the later slides. We have got a Phoenix LT rig, which is I believe managed or maintained by Darvick. It has a 50 kilonewton load cell. It can do direct cooling, so direct injection of LN2 through the nozzles. So that has the potential to reach up to 77 Kelvin, and the environment is air. It's not a vacuum chamber. And it has a window as well, so we could potentially do DIC on it as well, but we haven't really explored that at this stage. And the third rig we have got is a 100 kilonewton load cell. It's cryogen free rig, which can go down to theoretically 10 Kelvin. It uses cryo coolers to cool the sample through conduction. And the environment is, of course, at such low temperatures, you can't do any testing other than in vacuum. And I have some preliminary results that I'll present from this rig as well. So the Instron STS rig that we have, we have spent significant amount of time trying to deploy DIC on it, and there are some challenges with it. The first is because it's not a vacuum chamber. We have an issue of frost. And the way it works is that it has the inlet for liquid nitrogen, which by the time it comes to the chamber, it is in a gaseous form, and there is a fan at the back which circulates this cold gaseous nitrogen into the chamber. So you get convection effects, which affects your optical measurements. So that was a challenge. And the other challenge with regards to DIC is that, for example, if you're testing a material like 316, which remains very ductile even in cryogenic temperature, so we are talking about up to 50% gauge extension. So you start getting your speckle pattern which starts to crack, and speckle pattern acts as a strain witness. And if it starts to debond, then your strain measurements are essentially useless. So we have to develop a technique where we can do speckle pattern which can stretch up to 50-60% without cracking. We had to minimize frost, which we have done by better sealing the chamber, and then we tried to mitigate convection effects by installing computer fans so that we can create a laminar flow of air across the sample to kind of minimize these variation in the refractive index. So we have done all these kind of tweaks to the rigs, and we were able to kind of uh, get some initial DIC results. So this is just some example of the speckle pattern that is being deformed at the necking region up to 100% extension. So the way we do it is we create a discrete layer of black and white paint, and we use polarizers on our DIC cameras to cut down any reflection from the bare metal surface. Because the pattern is discrete, we don't get any significant cracking, even up to 100% extension. So this is what we develop as part of this study. And we did some quantitative analysis using different speckle quality parameters to see if, if there is any obvious cracking that we can't pick up from visual inspection. These are some of the results we generated from a 316L sample at room temperature and at minus 150 degrees centigrade with DIC. You can see on your right these stress strain curves. So the red curve represents the stress strain curve at minus 150, and the green one is at room temperature. And we did some uncertainty quantification to work out these error bounds in the strain values we are getting. So strains are significantly higher. The uncertainties in strains are significantly higher compared to room temperature because of the convection effect, even though we have got computer fans helping with the uniform flow across the sample, but still we have higher noise flow compared to room temperature. I think this characteristic two-stage hardening curve is well documented in the literature. We get initial strain hardening because of the slip planes moving, and then there is a region where you will get plastic flow, and then the strain induced Martensite transformation starts to kick in, where you then start to see a second stage strain hardening all the way up to failure. So compared to room temperature, you have a significant reduction in ductility, but still it's 316L, so it's still 50% gauge elongation at failure you'll witness even at low temperatures. So we started then looking at the strain fields that we get from the DIC, and even 316 is considered as, on a macro scale, it's a homogeneous material, but at cryogenic temp, even at room temperature, we do see slip band formation. So these are the maps for the first, the maximum principal strains at different elongations, starting from 0.5% all the way up to 20%. And you can see the evolution of strain field over the gauge length and a significant heterogeneity, which is caused by the band formation, the shear band formation. And on the right hand, basically we have converted these strain profiles into line profiles by averaging these strains along the width, and then plotting it against the gauge elongation to see the evolution of the deformation right up to the necking. So you can see clear horizontal streaks forming, which represents your shear band formation. Imagine if you have a extensometer, a clip-on extensometer or a strain gauge attached to the sample, you won't be able to pick that up. And at the bottom, we have the similar kind of strain maps and the evolution of strain field at minus 150 degrees centigrade. What is interesting in these ones is that close to about 8 to 10% for these particular sample, we do see a strain localization, which is very similar to what we see in the necking. And this corresponds to that plastic flow region that we see. So it is kind of like necking happening here before the Martensite transformation kicks in, which causes again a more spatially dispersed heterogeneity. So this is, I believe, the first time DIC is able to pick up this phenomena, even though this curve is well characterized in the in the literature, but we can visually see exactly what happens at this plastic flow region is essentially where, like, it creates a necking point um, prior to actual failure of the sample. So moving on to the even lower temperature. So specifically talking about close to 10 Kelvin. So we have this rig which does cooling of the sample through conduction using GM cryocoolers. I have a picture of the inside of the sample. So we've got some temperature sensors mounted onto the sample, and it has a window, so we can do stereo DIC on it as well. Again, with it's in all in vacuum, so we don't have to worry about frost or convection loops, but the speckle pattern cracking is still a potential issue that we tested for. So this test we ran at 13 Kelvin with stereo DIC, and we are able to kind of prove our methodology for speckle pattern creation to see whether we do see a cracking or not, and it was successful. This is the stress strain curve up to 18% elongation. Again, you see two-stage strain hardening with this discrete load drops that are again well documented in the literature, very low temperature for this austenitic stainless steel material. So we are still kind of, this work is in the preliminary stage. We are looking at what else we can do with this rig now that we are able to do stereo DIC at such low temperatures. We are also trying to integrate other strain diagnostics, so clip-on extensometer, strain gauges, to do a proper validation of our DIC results. And we are also looking at different methods of deploying temperature sensors as well, so we can start to pick up temperature gradients if there are any on the sample. So this is kind of work in progress. So just to summarize, we have enabled DIC measurements at temperatures as low as 10 kelvins. We are doing so we'd like to do it at temperatures close to 77 Kelvin in an environmental chamber, which is a much easier setup in terms of cost and time. But DIC bit is challenging, so we are trying to mitigate the noise floor, the convection effects to reduce the noise floor of the measurements. And then we are looking actively to expand our cryo-DIC capabilities to fracture toughness and more complex subcomponent level testing geometries, and looking at different materials as well. I think with this, I'm happy to take questions. Thank you.
Thanks, Khurram, for that for your presentation. Okay, so we don't have a huge amount of time left. If anybody has a question, you can put your hand up or just type it in the chat. We've got one question, which is about the DIC, I think, and it's just asking: is the paint that you're using, is it an off-the-shelf product, or is it something that you've had to develop specially for your
It's off-the-shelf acrylic paint.
Acrylic paint.
Okay. I don't see any other questions. I guess just from my thinking, maybe I missed it, but I mean, obviously you're dealing on the colder end of the temperature spectrum. How or who or when are you going to start looking at transients? I guess that's where you're going to end up with the biggest loading, right, on your sample. So
yep. Yeah, so we do have heaters on the grip, so we can in theory like create temperature gradient across the sample. So this is something we are looking into, how well we can do that and what should be the specimen geometry like, so we should be able to start doing it. I think the challenge is measuring the temperature gradient. There's no non-contact way of doing it. Like you have to have sensors on the gauge.
On the gauge.
Yeah, I think just one other thing. I mean, I'm not massively knowledgeable of fusion reactors, but obviously the temperature at the center of the plasma is 150 million Kelvin. But what is the actual temperature gradient we're experiencing in the surrounding material?
So the material in operating conditions can go up to 800 degrees centigrade.
Yeah, sorry, I think that was my microphone, actually. I think I have it on TV here. So we just have one more question at the moment from Matthew. So did you mention you had a leak check? You had to leak check some of the vessels, and how do you do these? How do you do this at this sort of temperature? Let me just mute.
I think we have we typically look for the vacuum we are able to generate. So there are pressure sensors on that we just monitor the pressure, and obviously sometimes you don't seal the chamber properly, so you would immediately know it's not building up the vacuum as you would like.
Okay. So I think unless there's any other questions, I think we can close the session. Thanks to our speakers, Khurram and Vicki, and I'd like to remind you that we have the next webinar in this series is on the 19th of May. So if you're interested, please register on the website. And thank you for joining.